For 88 years, every ship you watched pass through the Panama Canal was opened by a 730-ton gate driven by a machine that almost no one knows the name of. Edward Schildhauer designed it. A steel strut connected to a wheel 20 feet across, turning inside the lock wall, moving a gate that weighed 730 tons. The motor driving it produced 27 horsepower. Edward Schildhauer was born in New Holstein, Wisconsin, a town in eastern Wisconsin, small and German-speaking and practical, in the way that German immigrant communities in the upper Midwest tended to be practical, not given to abstraction, preferring problems that had solutions, preferring solutions that could be built. He studied engineering at the University of Wisconsin and came out of it in the manner of engineers trained in that period and place, capable of working at every level of a problem simultaneously, from the governing principle down to the tolerance on a single bearing surface. When the Isthmian Canal Commission came looking for the man who would be responsible for the mechanical and electrical systems of the Panama Canal, Schildhauer was the answer they arrived at. He was appointed Chief Electrical and Mechanical Engineer. In September 1907, he arrived in Panama. You felt it before you saw it clearly, standing inside the machinery space at Gatun Locks on September 26, 1913. The air close and salt-edged, the smell of new iron and tropical vegetation coming through the vents in the wall above you, the floor vibrating under your feet with a frequency that traveled up through your boots and into your chest before your mind had identified it as mechanical. The culverts running beneath the lock chamber floor were already open, Gatun Lake pushing water through passages cut into the concrete with a pressure that hummed through everything it touched. Through the access port in the lock wall, the water in the chamber was visible, already rising, no pumps driving it, only the weight of the lake above finding its level. The tugboat Gatun sat in the chamber and rose with it, riding water that climbed by gravity alone. There was no central control board that day. The board was not finished. Every valve in the system was operated by hand, by men standing at their stations reading water levels by eye, listening to the pressure in the culverts the way you listen to a room that has changed. The gate had to be opened manually, which meant that what happened next would happen by human judgment and Schildhauer's mechanism, with nothing else between them. The gate moved. It moved the way Schildhauer had calculated it would move, slowly, completely, without complaint. What he found there was a problem that had no precedent in the engineering literature. The lock gates for the Panama Canal would need to be the largest movable structures ever built to that point, 730 tons per leaf, standing 64 feet tall, at the deepest section of the canal, swinging through an arc in water at a scale that no prior canal had required. The designers of the Kiel Canal had not faced this. The engineers who built the locks on the St. Lawrence had not faced this. The Dutch, who had been building locks for centuries, had not faced this. Every mechanism that existed had been designed for a smaller problem. Schildhauer's problem was not a refinement of what came before. It was new. He had not designed this kind of mechanism before. No one had. Before he could put a line on paper, he needed to understand the full extent of what the existing world had attempted, what it had achieved, and precisely where it stopped. He needed to see those locks himself. Before he could design anything, Schildhauer had to find out what the world already knew. And in 1907, the world did not know very much. Schildhauer spent a year in Europe studying canal systems before he drew a single design for the Panama lock gates. He went to the Kiel Canal in Germany, which the Kaiser had ordered widened and deepened to allow warships to pass between the Baltic and the North Sea, a military project that had produced some of the largest locks in Europe at that time. He examined the Dutch locks, systems that had been refined across 3 centuries of hydraulic engineering in a country that had built its entire national existence on controlling water. He looked at what the French engineers who had previously attempted the Panama Project had left behind, and at every improvement the British had introduced to their colonial canal infrastructure in the preceding 40 years. He was not looking for answers. He already understood that no answer existed for his problem. He was looking for the edges, the point at which every other engineer who had attempted a problem adjacent to his had reached the limit of their design and stopped. He wanted to know exactly where the prior art ended, because that was where his work would have to begin. What he found was a consistent boundary. Every existing lock gate mechanism had been designed for gates that were lighter, shorter, and operating under lower water pressure than the Panama gates would require. The mechanisms that existed worked for what they were built to do. What they could not do was scale. You could not take the drive mechanism from the Kiel Canal's largest lock and multiply it for a gate twice as tall operating in tropical conditions under a lake that sat 85 feet above the canal and held more water than any man-made reservoir on Earth at that time. The numbers did not hold. The engineering did not transfer. Schildhauer came back from Europe with notebooks full of measurements, drawings, and operational records of systems that he could not use. He came back having eliminated every existing solution. What remained was the problem, and his pencil and a blank page. He had spent a year learning everything that had been done. Now he knew with precision what had not been done and what he would have to do himself. The mechanism Schildhauer designed was not complicated in its principles. It was precise. Those are different things. Inside the lock wall, in the machinery space cut into the concrete on either side of the gate, he placed a horizontal wheel 20 feet in diameter. Not a gear in the conventional sense, a bull wheel. A large diameter ring turned by a motor mounted beside it, the rim of the wheel moving at the speed the motor required. The wheel's diameter converting that rotational speed into the torque the job demanded. The motor itself was small, 27 horsepower per gate leaf, a figure that sounds wrong when you first hear it applied to a structure weighing 730 tons. The connection between the wheel and the gate was a steel strut, one end attached to a point on the rim of the bull wheel, the other end attached to the gate leaf itself. When the motor turned the wheel, the strut moved through an arc, and the gate, pinned at its top and bottom on vertical pintles set into the sill, swung with it. The geometry was not new. It was the same geometry that had been driving locomotive driving wheels since the 1840s. A rotating crank, a connecting rod, a swinging action transmitted from rotary motion to arc motion. What Schildhauer had done was recognize that this geometry, scaled up and oriented horizontally inside a lock wall, could swing a gate through water. The key to why 27 horsepower was sufficient lay not in the motor, but in the gate. Schildhauer designed the gate leaves as hollow structures, sealed chambers of steel plate, not solid-filled sections. A hollow steel gate leaf immersed in water is, by the physics of displacement, partly buoyant. The 730-ton gate was not hanging dead on its pintles. It was floating, partially, on the water it displaced. More than that, the gate was designed so that its center of gravity and center of buoyancy were positioned to keep the leaf nearly balanced on its pintles at every point in its swing. The bearings at the top and bottom carried the gate's weight, but they did not carry much of it, and the water, pressing on both faces of the gate from different sides, did a portion of the work of holding it in place. What the motor and strut had to actually move was not 730 tons of dead mass. It was a structure that was already nearly in equilibrium, displaced from that equilibrium by a fraction of a degree to begin the swing. The weight was real. What Schildhauer had done was make the machine forget it. Schildhauer had designed the visible mechanism, the bull wheel, the strut, the gate, But the canal's genius was in what was invisible. The lock chamber at Gatun was 1,000 feet long and 110 feet wide. When a ship entered the chamber and the gates closed behind it, the chamber needed to fill or drain to raise or lower the ship to the next level. At Gatun, going toward the Pacific, the ship rose 85 feet in 3 steps across 3 lock chambers. Each step required the lower chamber to fill with water from the chamber above it, or from Gatun Lake itself, until the levels equalized. No pumps did this. Gatun Lake sits above the canal at an elevation of 85 feet above sea level. It is a reservoir created by the damming of the Chagres River. At the time of its completion, the largest man-made lake on Earth. The lake's elevation is everything. That head of water is what drives the canal. Cut open the culverts, passages running through the floor and walls of the lock chamber, 30 feet below the water surface. Gatun Lake begins to fill the chamber. The water moves because water moves toward lower pressure. No electrical energy is consumed. No fuel burns. The lake falls fractionally, and the chamber rises to meet it. Schildhauer understood that the gate mechanism and the filling system were one design, not two. A gate that required enormous power to move would have demanded enormous motors, enormous electrical infrastructure, enormous maintenance loads on a system operating in tropical conditions. A gate that was nearly balanced, that moved on 27 horsepower, could be opened and closed hundreds of thousands of times without wearing the electrical system that served it. The filling system needed no power at all. The two principles reinforced each other. A 1,000-foot chamber filling in as little as 10 minutes by gravity, by a lake sitting 85 feet above the sea. The question was not whether it would work in theory. The question was what would happen when they actually opened the gates. The date was September 26th, 1913. The tugboat Gatun, a working vessel, not a ceremonial one, entered the first chamber at Gatun Locks, and the men who had built the mechanism prepared to find out what they had built. The central control board was not ready. It had not been installed. Every valve in the culvert system, every control for every mechanism in the chamber had to be operated by hand that day. Engineers and workers at their stations, watching the water, reading the gauge marks on the chamber walls, listening. The sound of water entering a culvert 30 feet below the surface is not a sound you can hear directly. You hear it through the floor, through the walls, through a pressure change in the air of the machinery space that tells you the volume is increasing. The men operating the valves that morning were working by a knowledge that was partly trained and partly intuitive, the kind of knowledge that takes months to acquire and cannot be written down. Schildhauer was there. The chamber filled. The Gatun rose. The water level in the chamber climbed toward the level of the water on the upper side of the gate, equalizing pressure across the leaf, because it was only when the pressure on both sides was equalized that the 27 horsepower motor could swing the gate without fighting the full weight of a lake behind it. The equalization was part of the design. The motor was sized for a gate that had already been relieved of the water pressure against it. When that equalization was complete, the strut engaged. The bull wheel turned and the gate moved. The motion was deliberate and unhurried, the mechanism inside the wall doing what it had been designed to do with a quietness that was, given the scale of what it was moving, almost unsettling. The first lockage of the Panama Canal was complete. No ceremony, no speeches. The tugboat Gatun passed through. The gate moved as Schildhauer had designed it, in a single smooth arc, 730 tons, describing a curve through the water, driven by a motor that would not have powered a small automobile. 4 days later, the earth moved. An earthquake struck the canal zone on September 30th, 1913, 4 days after the first lockage, while the Gotten locks were still in the early period of their operational life, before a full cycle of ships had passed through, before the mechanism had accumulated even a week of service hours. The shaking was felt across the isthmus. In a region of active seismic history, an earthquake on the canal zone was not a theoretical risk. It was a condition the canal would have to be able to survive for the duration of its operational life, which its designers intended to be very long. Schildhauer had not designed the gates specifically against earthquake loading in the way a modern seismic engineer would approach the problem. The discipline of seismic engineering as a systematic field barely existed in 1907 when he began his design work. What he had done was design a mechanism that was, in its fundamentals, simple. A gate hung on pintles, balanced on its own geometry, moved by a strut and wheel. The connections were solid. The pintles were set deep into concrete sills. The gate leaf, hollow and buoyant, was not a rigid system fighting external forces. It was a system in equilibrium, and systems in equilibrium are, in the engineering sense, naturally stable. The gates held. Every gate held alignment. Every pintle held its sill. The bullwheel mechanism, sitting inside the lock wall in its concrete housing, absorbed the shaking and returned to its position. The first trial lockage had proved that the mechanism worked. The earthquake proved something more difficult to design for, that it endured. 4 days. That was the margin between the first time the gates moved and the first time they were tested by the earth itself. Both times they held. The canal opened officially on August 15, 1914. After that, the mechanism ran. It ran through the morning of every day the canal was open, which was most days, in a climate that corroded iron and exhausted rubber seals and worked grease out of fittings and pushed tropical vegetation into every gap in every structure that stood still long enough. The Zonians, the American workers and engineers who operated and maintained the canal under the authority of the Canal Zone Administration, inherited Schildhauer's mechanism and learned it the way a man learns any complex machine he runs every day. First by the manual, then by the machine itself, and finally by a body of knowledge that exists nowhere in writing and cannot be transmitted except by working alongside the man who already has it. A gate operator at Gate and Locks in 1940 knew things about that mechanism that Schildhauer had not written down, not because Schildhauer had failed to document it, but because the knowledge had accumulated in operation, in the decades between design and practice. He knew which gate swung slightly slower on cool mornings when the grease in the pintle bearings had stiffened in the night air. He knew the sound the strut made when the connection to the gate was correctly seated versus when it needed attention. He knew the rhythm of the culvert pressures, the way the water in the chamber spoke to the valves through the floor of the machinery space. He knew this the way an engine room man knows a boiler that has been his responsibility for 15 years, not as a system described in a manual, but as a thing with a character, a thing that told you what it needed if you were willing to listen. Every ship that passed through Gotten Locks passed through on the knowledge of the man who designed the mechanism and the men who learned to run it. By 1960, some of those men had been running the same mechanism for 30 years. They did not think about Schildhauer. They thought about the gate. The canal opened in 1914. Schildhauer's mechanism was there. It was there in 1918, when Atlantic convoys were moving war material and the bull wheels turned without knowing it. It was there in 1941, when the Pacific Fleet was gone, and the canal became one of the most strategically important points on Earth. It was there in 1956, when the container revolution had not yet arrived, and every ship that passed still moved breakbulk cargo in wooden crates. It was there in 1977, when the Carter administration, Tollikainen, signed the treaty that would transfer the canal to Panama, and the Zonians, who had run the locks for 20 or 30 years, began to understand that the world they had built their lives around was going to end. The bull wheels did not know any of this. The struts turned, the gates swung. 730 tons, 27 horsepower, 10 minutes to fill a chamber. The mechanism Schildhauer had designed in 1907, on the far side of a year spent in European canal systems, learning what the world could not yet do, ran in 1990 without fundamental change. It ran in 1995. It ran in 1999. In December 1999, the United States formally transferred the canal to the Republic of Panama. The gates were still Schildhauer's gates. In 2001, the last American Zonians left the canal zone. The bull wheels were still turning. In 2002, the Panama Canal Authority replaced the bull wheel drives. Hydraulic actuators. New machinery. A different design. The decision was reasonable. The canal needed to increase its operational capacity. Hydraulic systems offered advantages in force delivery, in maintenance profiles, in the ability to modulate pressure at every point in the gate's arc. The engineers who made the decision in 2002 were not wrong. The bull wheels came out. The steel struts came out. The 27 horsepower motors came out. The horizontal wheels that Schildhauer had designed in the period 1907 to 1909, that had been installed before August 15, 1914, that had run through 2 world wars and a Great Depression and a Cold War and a treaty negotiation and a canal transfer, that had moved 800,000 ships. Those wheels were removed from the machinery spaces in the lock walls at Gotten Locks and at Miraflores Locks and at Pedro Miguel Locks, and taken out of service. The machinery spaces were refitted. The new hydraulic systems went in. The gates still moved. The ships still rose and fell. The water still filled by gravity. Still took 10 minutes, still required no pumps. But the mechanism was different now. What replaced Schildhauer's design does not carry his name. It does not carry any name most people know. It is the system the canal runs on today. It works. The mechanism ran for 88 years. No redesign, no fundamental change. Then it stopped. There is an observation deck at Gatun Locks. Visitors stand on it and watch the gates move. 730 tons swinging through the water, a curve described so slowly it is hard to believe it is moving at all, until you look away and look back, and the angle has changed. The tourists take photographs. The cruise passengers press against the railing. The ships go through. Schildhauer's name is not on any interpretive panel at Gatun Locks. It is not on any panel at Miraflores Locks or at Pedro Miguel Locks. The panels describe the canal. They name Goethals. They explain how the water rises. They do not name the mechanism. They do not name the man who designed it. His biography exists. The University of Wisconsin alumni records contain it. He was born in New Holstein, Wisconsin. He studied engineering. He was appointed Chief Electrical and Mechanical Engineer of the Isthmian Canal Commission. He spent a year in Europe. He designed a mechanism with no prior model. He filed patents. After Panama, he returned to the United States. He entered business. He entered Los Angeles politics. He lived the life a man lives after he has done the largest work he will ever do. He died having designed one of the most durable mechanisms in American industrial history. The mechanism ran for 88 years, 800,000 ships. Almost no one knows his name. The visitors at Gatun Locks watch the gates move and do not know whose work they are watching. The water fills the chamber. The struts turn. Different struts now, hydraulic, installed in 2002. The gates swing. The ships rise. Schildhauer's name is not on the wall. There were men at those controls in 2001 and 2002 who had been running Schildhauer's mechanism for decades. Some of them knew the history, Most did not. It did not matter to running the gate. What mattered was the gate, the resistance in the strut connection, the sound of the culvert pressure, the gauge on the chamber wall, the ship waiting in the lock. They were the last operators of that mechanism. They did not know they were the last. Or some of them did, because the handover was visible, the new hydraulic system was being installed in stages. Some of them watched it happen, watched the bull wheels come out, watched something they had run for 20 or 30 years be removed from the machinery space where it had operated since before their fathers were born. What they knew, they passed on. Some of it was written down. Most of it went with them. That kind of knowledge does not transfer to a manual. It transfers from one man to the next, standing at the same controls, watching what the other man's hands do. If you worked on canal or lock machinery or worked anywhere that still ran equipment from the early 1900s without fundamental change, we want to know what that was like. If you have seen the Panama Canal gates moving, from the observation deck at Gatun, from a ship going through, from anywhere along the canal, tell us what it looked like from where you were standing. And if there is a mechanism from this era in your town, your county, your state, still running, still holding, or pulled out and sitting somewhere quiet, a mechanism tied to a specific engineer whose name the history books haven't found yet, leave it in the comments. We will find it